Yeah, definition is perfect, but this example, now wonderful. Yeah. This is very calculated with this.
Okay. So, given a compact group, we ask several questions on. We want to ask similar questions for quantum groups also. So,
Q power.
no, this is an operator. So, n is an operator. So, it is this function by function calculus.
Q power.
So, Q power n. So, if you like, I can write it explicitly. Q power n En is Q power n. That's how it is. So, this is a fast result. So,
But also L is in the first one.
yes,
Phi of alpha. L is in the left, right?
yes.
So your definition of L, you have to make a zero as
Zero is killed. Zero is killed. Zero is killed.
You didn't write that. That's what I meant.
Yeah, that is assumed.
L seems to be on the
That
right.
is-
Phi n, phi beta.
That is assumed that maybe.
Same L, but has different properties because one is a one-sided.
Sure,
other is a two-sided.
sure. So let us emphasize the point which KBS is making. That is the following. So you may notice and you will see these more elaborate, meaning not more elaborate versions of these structures tomorrow. So L2 of n I can think of as a semi-group or inside a group Z. Here I am having translations, meaning I am adding some element. So En goes to En minus 1, meaning I am adding some element. And then there is a point here where this addition goes out of this space. So whenever such a thing happens to be here tomorrow, you should interpret that operator is 0. That is 0. So it will happen. This notation will come much more frequently in a much more complicated way, but it is always interpreted as it is 0. But we will use the same notation. It gives some notation of advantage maybe in doing calculations. So whatever I will do tomorrow is really much more elaborate understanding of objects like this, meaning semi-groups sitting in groups, essentially. Discrete semi-groups, discrete abelian semi-groups sitting within groups.
L acts on L to Z or L to N?
Both.
They acts on both. They acts on both. I am using the same
One side
notation.
and one the other side of the other. Yeah.
They acts on.
That is what we.
So this one, there is L on this, here it is on that.
L operator acts on both the
Both the spaces by the same prescription.
By the same symbol, it is the same operator.
N goes to N minus
A is not normal, right?
N is not normal, beta is normal. So what on N to Z, N is immediate. On N to Z, N is immediate.
The other one is isometric.
Yeah.
So N to Z is
Unilateral shift and bilateral shift. So both here are using the same L.
Ah,
All designed to keep the students awake.
what?
All designed to keep the students awake. It's challenge.
Which channel?
Flexibility of thinking this way, that way, saying that.
No, it is not. It is otherwise you use two symbols and then meaning. If you have 40 of them, then you get really confused now. And that will come tomorrow. Therefore, there is no way you can escape them. Otherwise, you have to parameterize them with really very complicated objects.
This is a warm up for the real business.
Yeah, maybe this was done really long back. On the other hand, whatever I will talk about was published last year. Therefore, yeah, but these are really much simpler versions. These are simpler versions. So complicated things will have many such sheets which are indexed by actually objects underlying that group. So maybe at that time we may need that. Right now, I am skipping it. Even today we may see something slightly complicated. When you are given a compact quantum group, G, that actually means I have an algebra which I denote by CG. Okay? Given a compact quantum group G, I mean I have an algebra CG and a co-multiplication. This is again just a notation. It is not necessarily commutative or anything like that. It is just a notation. There exists a unique state H So it is a functional from CG to C such that identity tensor H delta A equals H tensor identity delta X equal to H of A times 1. Let us think for a minute what does this equation mean. Let us think for a moment what does this equation mean. So what is this? If in case A equal to CG or some compact group G, in case it is indeed so, then H is a linear functional. That means H of f is actually integral f d mu for some probability measure mu. And so what is one tensor H delta of f? This is nothing but integral f g prime g mu of g prime. The other quantity is H is given by this integral with respect to mu. So H tensor 1 delta of f is equal to integral f g prime g mu of g, and these two are same as integral f g mu of g. Therefore, this condition
evaluated as G comma G prime.
is no, it is not G comma G prime. It is on one element really, right? Because this is skilled. This is an element in delta A. G. It is on G. Here it is on G prime. Both of them are same. So this condition is indeed a translation of this left and right invariance condition of the Hahn measure. Therefore, we call such a state is called the Hahn state. Let me quickly write it down for the SU2 example. So, H of A equal to summation Q to the power 2I EI 0 EI0 is really this element. EI tensor is 0 in N2 of N tensor N2 of Z. Sorry. It is, I have to normalize so that it becomes such as 1 minus q square. 1 minus q square times this is the Hahn state in this example. In the CG case you already know, in the C or star G case also you have already seen it is evaluation at the identity. Maybe I
So
should
SU2 is the, like you never mentioned, but that alpha and beta, that was SU2.
what?
Like you never wrote down what was SU2. I mean, you said it in terms of alpha and beta, but it was like the notes.
You didn't name it as SU2.
What?
You didn't name it as SU2.
Oh, I see. I'm sorry. So whatever I described in that that example, you may notice that why is it called SU2? Because in these relations, if I put Q equal to 1, then it follows that beta is normal, that means beta is given by a complex number. Alpha will also become normal, so alpha will also be given by a complex number, and those conditions will imply that if beta is given by Z, alpha is given by W, then their norm squares is 1. So this is really a matrix in SU2, therefore this terminology. So we stop here. In the next class we will introduce the concept of representation and probably the invariant which we want to talk of, and eventually I should be able to formulate a very precise question which I think can be answered not very difficultly. It should be fairly easy, but we have not pursued, so that if you are interested you can try to do it on your own to